Acid. The green corrosive death juice has been dissolving bodies and creating iconic comic book villains since the 40s. In this video, we'll be teaching you about what acids really are, as well as their antagonist, the bases. We hope you enjoy and learn something new.
Acids are proton donors. There are other definitions for an acid, but that's the one you most commonly use. Now, I'll explain this with an example. When you think of hydrochloric acid, you tend to think of HCl dissolved in water. Perhaps like this, that's a beaker of water, you can see the HCl is dotted around. This is wrong. What actually happens is the HCl will dissociate when dissolved, turning into H plus and Cl minus ions. And you will get something like this instead, where the H plus and Cl minus ions float around the water. Now H plus is a proton without any electrons, therefore H plus is just a proton. Acids will give away this H plus, essentially making them proton donors, as the definition says. To compare acids, we use a thing called the pH scale, which is the power of hydrogen. A lower number on this scale means the solution is more acidic. The scale tends to go between 0 and 14. It's a logarithmic scale, so one number lower is 10 times more hydrogen ions within the solution. Now we have a solution of water, which is normally a neutral solution. Neutral at room temperature and pressure would be pH 7. So it takes a pH probe, dip it in, gives a fluctuating value about 6, ranging from about 6.4 to 6.1. Now again, room temperature and pressure neutral would be 7. This is not because the carbon dioxide from the atmosphere is dissolved in the water only slightly, but that makes the solution mildly acidic as you get 6. Now here we have hydrochloric acid, a strong acid. Dip this in. It's a very strong acid. Now I did say again, normally from 0 to 14. Clearly not always from 0 to 14. It's a very low number, so very strong acid. Now the first factor we'll go over which can affect pH is the strength of the acid. Now the strength of the acid is essentially how much the acid splits up, how much their molecule splits up. So HCl, as we showed earlier, splits into H plus ions and Cl minus ions. HCl splits up completely, however some acids don't. Some acids stay as their full acid form, their molecule. Now sulfuric acid dissociates a lot, and it's a strong acid, so it's just in the minus. However, if I show you a weak acid, ethanoic acid, which you will find in vinegar, again, weak acid does not dissociate fully. So it's got a slightly higher pH because it's less acidic. The second factor that affects the pH of an acid is the concentration. An acid with a higher concentration would have a higher amount of H plus ions, and therefore a lower pH. More concentrated acids will react more vigorously. To show this, we have dilute and concentrated sulfuric acid. And we'll be reacting both of them with potassium bromide. Now this is the dilute first, 1 molar sulfuric acid. And nothing happens. It's very unreactive due to the much less H plus ions than is in this. This is concentrated sulfuric acid, and the reason I am wearing gloves. You can already see the reaction of the color change. bubbling, just some gas being produced. And bromine vapor is being produced as one of the products, alongside some other vapors and other products. As you can see, a clear difference between the reactions of dilute sulfuric, basically doing nothing, and the concentrated reacting much more vigorously. Above pH 7, you have alkalis. Alkalis are just soluble bases, and a base is a proton acceptor. Now, alkalis, like acids, dissociate, so you get some which dissociate fully and some which don't, so obviously creating strong and weak alkalis, which again affects their pH. Now, here I have sodium hydroxide and ammonia solution. Sodium hydroxide is a very strong base. Do not get in your eyes, you will never be able to see it again. Now this has a pH of 13.4. Very strong stuff, and that's relatively dilute as well. Now, ammonia is a weaker base. 10.7. So what do you reckon happens when you mix a base and an acid together? So when you react an acid with an alkali, you get salt and water. For example, we take hydrochloric acid and sodium hydroxide, creating sodium chloride, a common salt, and water. This is, you probably know this, you've probably seen this before. If you haven't, then done something already. Now, you might remember state symbols from one of our previous videos. They're quite important, particularly for these reactions. Now, 3 of these are aqueous, they're still dissolved in the water, and the water that's created is a liquid. Since they're dissolved, they've dissociated, so we can write this equation in form of ions, making an ionic equation. So we start with the H+, which is aqueous. State symbol is still very important for this bit. The chloride ion, sodium plus ion, hydroxide. Hydroxide is a compound ion with an oxygen and hydrogen. It's got a charge of 1-. I am running out of space a little bit. That's okay. I'm going to write this very badly. Don't do this, guys. We've got sodium, chloride again, and water does not split up. It does slightly, but it mostly doesn't split up. So you see, most of these are aqueous. Now, what we can do with an ionic equation is you can cancel out things that don't change state. For example, the chloride is aqueous on both sides, as is the sodium. The water and the hydroxide are bonded to form the hydrogen, and the hydroxide bonded to form the water. So we can rewrite the equation in its proper form after we've got rid of the spectator ions, like this. And that is what actually happens, that's the reaction itself. In quick mind, you've got the proton being given to the hydroxide. The acid is acting as the proton donor to create water. Now, I can show us again the different acid-alkali reaction. Here I've got sulfuric acid, potassium hydroxide to make potassium sulfate, and water. This balances slightly differently, as you can see by the 2's there and there. This is because of the 2 hydrogens that are donated. Now, you can write this after we got rid of the spectator ions, which would be the potassium and the sulfate ion. We can write this this, and you can see all the 2's the same on all 3 molecules, so you might as well just get rid of those and you get the exact same equation. Acid plus alkali equals salt plus water. Acids and bases can be found regularly in everyday life. Here we've got some examples. Vinegar is an acid, it's about pH 2.5. The actual acid is ethanoic acid or acetic acid, as it's sometimes called. Obviously you use it quite a lot for cooking, cleaning, putting on your chips, you know. Limes. You've probably heard of citric acid, which you find in a lot of citrus fruits. The pH can range depending on the fruit. Limes are generally estimated to be about pH 2 to 3, so quite acidic. We've got milk. Milk contains lactic acid. It is barely acidic, it's about pH 6.5 to 7, 7 being neutral at room temperature and pressure. So barely acidic, but just slightly. Bleach. Now bleach is a base. When it reacts with water, it forms acids which you use to disinfect stuff around your house. The bleach itself is a base. And now we've got drain opener. Drain opener is a solid base. The actual base part of it is sodium hydroxide, a very strong base as we mentioned before, but unlike before in solution, this is in solid form. So not all of you will have access to a pH probe that I've shown in the previous clips. Other ways of measuring acidity or pH include indicators like, say, universal indicator, phenolphthalein over here, and litmus paper. We're going to start with litmus paper. So litmus paper is quite simple. It just turns red in acid, or the blue litmus paper turns red in acid, as shown. You see, that is nitric acid, 2 molar nitric acid. And the red litmus paper will turn blue in an alkaline solution. That is 0.5 molar sodium hydroxide, the strong alkali. Now those just tell you if it's an acid or an alkali. They don't tell you how strong or how dilute. That's the actual indicators which will give you a guide to the pH. This is a universal indicator. Now, a universal indicator is not particularly nice because, as you should hopefully see, it kind of has a colour gradient. So that's a strong acid, nitric acid. This is not enough in the pipette. This is a weaker acid, ethanoic. Now that's red, that's orange. Now if we go to a weak base, might be stronger than I thought. A weak, relatively weak base. Ammonia goes a purplish colour. And sodium hydroxide goes a much darker purple colour. Now the I'm going to have to empty this beaker. Now if we were to use the universal indicator to demonstrate a neutral solution, we should get green. Now this beaker did have nitric acid in it a few minutes ago, so it might not be perfect. It'll be the same green as you get in the bottle. There you go, green. Now this scale from red to purple, it's very hard to determine the accurate pH because obviously it's a scale and it's quite hard to pinpoint where the colours actually are. Some other indicators we could use to overcome that issue include things like phenolphthalein, which is one of the worst things in the world to spell, and methyl orange. Once you get to doing titrations, you will see these quite a bit. Phenolphthalein turns pink, turns from colourless to pink in a acidic solution, whereas methyl orange, I underestimated the amount of beakers I need. whereas methyl orange goes from orange, still some kind of gradient, it's sort of yellow, orange, red. It should go, I can't remember, because we all use green thing. This will be a surprise for both of us, all of us. It goes red. Now, we often use these in titrations, as I've said, and you'll often be told that the pH it changes out is around pH 7 or neutral, as the water would, as water is, sorry. But that is not true, as you'll find out at A-level chemistry, should you choose to take it. Phenolphthalein will often change around 8 to 9, and methyl orange changes around 4.5, pH 4.5. Yeah, but indicators are very useful for working out the pH of things and neutralization points of things. One thing you can try at home, you can look up how to make an indicator from red cabbage. It's very interesting, quite fun. Yeah, it's good fun. And that's all for the acid-base video, guys. We hope you enjoyed the video, and remember to stay sciencey.